Okay.
Okay.
Yeah.
I was trying. Yesterday I tried to fix
Yeah.
that situation. I was not able, but
Okay.
I tried to feed this
See,
some
actually,
this
that day itself, I reflected and again, means then I thought that okay, why do want to change the direction of horn? We can change the
yes.
direction of instead we can change the direction of reflectarray so that
Okay.
port will be remain the same coordinate system, so it will not create a problem for us, right? So what
Yes.
we'll do is we will keep a horn as a same position, okay? With the same position, we
Okay.
will have feed with the wavegate port, okay? And then
Okay.
we can rotate the reflectarray wherever. For example, if you want to feed offset feed us, for example, 30-degree horn, okay?
Okay.
So shall I 1 minute? Let me share my screen and then explain you okay, how
All
we
right,
are
sir.
going to
Okay.
explain. Let me
Oh, that's
explain to
good.
you.
So let me just
So shall I
stop.
share my screen?
Yeah, sure.
Okay. So
You
can
can
you see
stop
my
it.
screen? Can you see
Yes.
my screen? Yeah. Okay.
Yes.
So now we have yeah, horn. Sorry. Oh, sorry. Um, let's say we have this is the horn. Okay. Uh,
Yes.
okay. Then we have a reflector array here, right?
Yes.
Reflector array here, right? Okay. So
Yes.
this horn, no, we are going to rotate like this, right? Correct. For example, we are going to move this horn to some, for example, X and Y axis like this, and then it
Exactly.
will point towards like this, right? Offset front
Yes.
reflector, or in this
Yes.
fashion also. Okay. Okay. So
Yes.
instead, so we are facing the issue of, for example, so we are facing the issue of that because for example, so the coordinate system is like this, something like this. Okay. So,
Okay.
but the Waveguide port will work along with the coordinate system only. So when you move
Ex
this, then it is finding, for example, see, according to them, we are giving coordinate port to position and everything, right? So while
yes.
simulating, it will take only that as a reference. That's why it could not able to simulate and then giving so instead, what I will do. So we want, for example, this refractory it should be focusing like this, right? It's 30-degree,
Yes.
correct? Correct. So instead, what we can do is, we can move this reflector to in this direction, okay, in this fashion,
Okay.
okay, maybe in this fashion, okay. We'll
Okay.
have in this fashion, okay. So it is remain, you can see here, it is remain pointing towards like this. So for example, instead of
Okay.
rotating this on to here, okay, for example, 30-degree, okay. Instead of doing
Okay.
that, we are going to rotate this reflector as 30-degree. Okay.
30-degree.
So then
Oh,
it will become like this, right? So,
yes.
but the position should be optimized in order to see that okay, this horn is in for that particular position. So horn will be remain facing the same direction, but when you look at this reflector ray, it will be pointing like this. Then horn you can see here it is again 30-degree we are good able to achieve, but it will be tricky because we have to offset the horn, offset the reflector ray here and there in order to we have to offset the reflector ray, we have to rotate the reflector ray by for example 30-degree, and also offset by for example uh, whatever dimension we have xy in the xy coordinates, okay, we have to do that.
Yes.
Correct. So in
Yes.
XY coordinates, see, for example, this is the XY coordinate system. Okay. So here you can see here this is the X, this is Y, and then you have a yeah, reflector array like this, right? So reflector array like this,
Yes.
right? So now we are going to rotate this, right? So for example, then accordingly we have to rotation is should not be a problem, but only the thing is that we have to offset position, right? In terms of X
Yes.
and Y that we need to maintain. That's it. Okay.
Oh, that's
This
good.
is one idea. Yeah,
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 that's a good
yeah.
idea.
This is,
I think
yeah,
we are able to do it. To do it.
yeah.
Okay.
But we should ensure that um, how much offset we are having, and this one, how much uh, how much degree should not be a problem because angle should not be a problem. Only the thing is the offset is a tricky part there. Okay. Yeah.
Yes, sir. So this one I tried yesterday to feed. Yesterday night,
Okay.
I tried to feed this one using the macro. The
Okay.
macro, yes, the Gaussian beam. So I tried to use to feed this one with Gaussian beam, but because
Okay.
I did not take a lot, enough sample, because I just took just 5 samples,
Okay.
I was just confused. You know why? Because when I feed it with the Gaussian beam, it look like it has same property with plane wave, because actually they are just feeding on the back of the array. The feed is like from the back
No,
of
no,
the
it shouldn't
array.
be
You
front,
see?
right? Should be
So
fed
yeah.
front.
So as long as I did not take the enough samples, I just took just 5 samples to test. You know, this is the beam I just got, which
Oh,
is not, yeah. So it can give me some reflection
yeah.
from, yeah, it can give me
But
some,
you are feeding behind the ground plane or just above the reflector.
it's like behind the ground.
No, 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 no. It should not be the case, right? Because it will reflect, right? But how come you are getting the beam? So can you go to that far field source, please?
Okay, this one,
No, no, field sources, field sources.
this
Whatever you
one.
are telling about. Yeah, this one. Can you click open?
I think it cannot open.
Right. Oh, right
Yeah.
click. It's just you just imported this.
No, yeah, this one is like I use some. Uh, hold on. I see how it looks like. It's how it looks like. This one I use some this MATLAB formula.
Oh,
I
great.
tried. Yeah, I use this MATLAB formula to calculate the Gaussian wave, and
Okay.
then I can try to calculate the distance to like everything from here, and then when I get
But then here you
this
can
spot.
control the direction as well, right? You can
Yes, I
control
can
the
control the
direction.
direction. I can control the
Okay.
direction and everything from here. You know, this is, for
Okay.
example, this is the distance, you know, the focus distance from the field structure.
Okay.
So I can
Um,
do, MATLAB will give
as far
me
as I can see
the
that
parameter.
it's a plane wave, right? Plane wave kind of thing, right?
It's kind of plane wave, but it's not a plane wave.
But Gaussian wave should not be a plane. It will be a kind of spherical wave, right?
Yeah,
Okay.
but
Can you go
mostly,
back to? Yeah.
actually, I've seen many papers that they use the same method to feed. So I don't know if is it
No, no,
correct
no.
or
Actually,
it's
see,
just
there is one analysis is there, Gaussian beam analysis. Okay, but which is
okay.
very good analysis for the, for example, spot beam. If you want to have a spot beams and also the reconfigurable beams, the other stuff. No, so in order to analyze that, they use Gaussian beam analysis. That is theoretically it is proven, and then it is most of the time no for contour beam. Correct. So, for example, shaped beam, right? So, for example,
Yeah.
if you want to shape the beam the to focus to only Canada or US or India or anywhere. Okay, so we have to shape the beams, right? That
Yes.
point of time they use this kind of beams, Gaussian beam analysis. Okay, so now can you check just rotate right side, please? Or can you give me control, please, so that I will check,
Okay. All right.
where it is getting feeded. Oh, it is. I think it is feeding at this position only. Okay, so means. Uh, the arrow is this direction, right? Okay, W
Yes.
in this direction. And let me check. There is reflector. Why it's not showing that?
Oh, okay. Because I selected the feed. That's why. That's why
But
we
I have
cannot see.
but I have selected a reflector also, but still it is showing the same.
Let me try. Because I selected this feed. Perfect. Let's do feed again.
Field sources that is there.
Yes. Field sources Gaussian. Because we select this, we need to.
Hide this. Can you hide this?
It's hidden. Let me just
But still
show
it's
it.
showing that, right? Oh, okay, okay,
Yes.
okay. Sorry, sorry, sorry. No, 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 no. Wait, 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 wait. Now it will show you. Okay. I was confused. Okay. Oh,
Yes.
okay. You see, can you see here? Okay, this is the reflector, and then this is the reflector, right? So in this
Yeah.
view, we'll see. Okay. So then it's fine. No problem.
We can feed with this.
Yeah, yeah, we can feed like this. Yeah, no problem. See, unless you don't have any, for example, phase shift, if it is a plane wave, we can just excite like this. Okay. But if you have, so you are exciting it just above the reflector area, right? Correct?
Yes, actually, when I do parameters, I have a possibility to control even the distance.
Oh, okay.
Yeah, I
But
can show you.
here it
I
is
can.
actually zero distance, right? I mean, just above
Yes,
the reflector.
this is like this zero distance. I
Just 1
can.
minute. I let me check. This is
Okay.
arrow. Where is this arrow going? Just um. So it is basically, 1 minute, 1 minute, 1 minute.
Okay.
Uh, it's horizontal, right? Okay,
Me.
just 1 minute. Okay, okay, vertical. So it is a plane wave only. So um, if you animate this, no, then we will come to know. So it's a plane wave. That's why you are getting means very good, very nice beam basically. Um, if you look at here, okay, just a moment.
Yes.
Oh, okay, we are getting this head up beam, right? So
Yes.
35 directivity is 35, but this is as expected, right? Correct?
Yes. I think so.
Yeah, yeah. It is as expected. Okay. So you are exciting the plane wave and then you are trying to find out. Actually, one more thing you can also analyze this. For example, in 2D, no, correct? 2D.
Yes.
So if you go to, you can do the phase analysis as well. Okay, phase pattern as well. You just look at this. A field. Yeah, phase. Okay, phase is not there. Okay. Mm, can you see here
Yes.
how the fields are getting, but in the phase we have to see. Uh, I thought of, seeing the fields on the plane. Yeah, no, we can do something like, phase analysis, right? Also. Okay.
Yes.
So, oh, real and imaginary part we are getting. Okay. So if you animate this field and can't put contour and then dB. Yeah, now we can see the phase plot as well. Can you see here? So
Yes.
now we can able to understand. So what phase distribution we are getting, that also possible. Okay. Uh,
Okay.
so can you see here? Uh,
Yes.
phase fields on the plane. Which plane we have to see? Maybe cross section B. No, cross section C. Okay, just a moment. Oh, you run so many simulations, right? So
Yeah.
that's why
Yeah.
system is getting stuck. So we can able to see the phase as well. Okay. So that
Yes.
we'll come to know whether, see, for example, you are expecting some phase in particular position, right? Phase to be
Yes.
compensated. Whether it is really compensating, that element is really compensating for that particular phase or not, that we can validate here. Okay. But one
Yeah.
ambiguity times in here is 0 to 360, but it is showing us oh, but it is showing us 1 to 360, but I don't know why it is only red.
Yeah.
0 degree is red. That is, excitation phase. But we have to see the phase on the uh, plane. Basically, just a moment. It could be. So what I'm trying to show here is like, for example, z-axis now. If we
Yes.
just, move the position that of that cut plane to that particular position, no, we'll just look at the phase distribution on the just on the basically, uh, on the refractory surface, just above the refractory surface. What is the phase distribution we are getting? That way we can able to make out that, okay, yes, that particular element is compensating for that particular phase. Okay.
Okay. Okay. I can see.
Getting my point? Getting my point?
I get it.
Okay. So maybe in the this cut plane will not work. So maybe do it all cross sections. This refers to 0 degree. Okay.
Okay.
Or maybe this face itself, within 50 degree. That is why it is showing as a red. That is also possible. Okay. So
Okay.
it's also possible. Let's see. Oh, sorry.
I think if I had more, for example, if I had more sample when I'm trying to put um to calculate the Gaussian equation, if I
Yeah,
had
yeah,
more sample, I will have very good beam shape.
correct, correct.
Yes.
Second thing
Because
is
I
that,
just
did you plot that Gaussian beam in MATLAB itself?
no, I didn't plot it. I
But
just do
please do
calculation.
that because, because it is exciting the only plane wave. But it is a good way to estimate the, for example, see, can you open a paint for me? Yeah,
Yes.
here. Yeah, correct. So let's say, shall I delete this one or?
Yes, sure.
So here you can see that, maybe we have a reflector, right? So
Yes.
now I'm going to see I have sorry, not this. I have a, one, for example, element size versus, yeah, S
Yes.
curve is there, right? Element size
Exactly.
versus space. Okay. Now I am going to, as I have phase distribution along X, what the phase to be compensated along Y. Okay. So in 2D,
Yes.
this 2D plane, what phase I have to compensate. So I am after placing the element, right? According to the phase distribution, I just, I have pasted the element and then all that's done. Now this in this particular simulation, no, what we can validate is when you excite the plane wave alone, okay, plane wave, okay, not the
Exactly.
Gaussian beam, or okay,
Yes.
then what will it whatever it reflects, right? Because we are exciting only the plane wave. So whatever it reflect, that is the phase. That is it compensate for. Correct?
Okay.
That is the phase it compensate for because we are exciting the plane wave, and then whatever gets reflected, right? The phase,
Yes.
for example, this particular unit cell, maybe in the S curve, maybe it is generating 220 degree. Okay, for
Yes.
example. Okay, and this particular unit cell in size is generating 200 degree, let's say. Okay, so whatever
Yes.
get reflected, no, on this one, it will not be across exactly 220 degree because we are not doing the practical simulation considering the size around the because we are only following the Flockert port unit cell approach where we consider unit cell size, unit cell is placed in presence of same sized element basically. That is Flockert port one. Oh, correct? Okay.
Yes.
Okay, that this is how we are analyzing now. Okay, for example, rocket pod analysis, how it will does is it assume that infinite array approach. Infinitely, this element is extending, and I'm estimating the reflection phase for this particular element. That is how it will estimate in CST or any tool. Okay, here, for example, in this particular simulation, unit cell simulation, we are getting 220 degree for that particular size. But in reality, it will not be 220 degree. It will be can be plus minus 10 or plus minus 15. That is there, right? So when I excite my plane wave here, and then what I will get back is, for example, 220 degree for this particular element, approximately 220 degree plus minus that, and
Yes.
here it will be 200 degree, correct? So in this
Yes. Correct.
experiment, no, we can able to maintain that we shall able to 1 second. Sorry, I got a call, so that's why.
It's okay, sir. It's okay,
Yeah,
no
yeah,
problem.
yeah, yeah. Yeah, yeah. What is your opinion? Did you get my point? What I'm trying to say? Actually, yeah,
Yes,
we can go. Yeah,
I get
you
it.
can proceed. You can proceed. You know, it is taking time, taking for a while. So, can you plot that Gaussian beam in MATLAB itself?
I think it's possible. It's
Yeah, yeah,
possible to plot it, but
yeah.
maybe we'll take time because this is the question.
No, no, no. Just take that equation outside, maybe in live script like that. We can just plot that Gaussian beam itself. By looking at that itself, we can able to find out d square plus zr square. Okay, okay, okay. Zr square is what you are taking is 3.17 is what?
Which one?
W naught.
Oh, sorry. This is just this is the 3.71 is that we need to calculate to get the size, it's just to get the size of the array. So
Okay,
it's
okay,
it's
okay.
give the exact beam source, because if we did not calculate the w0, that will be difficult for us to fit exactly, because this is according to array size. For example, I can
Okay.
show you how it works. I don't know why it's initializing.
Yeah, yeah, yeah. It's taking much time basically.
Because if we did not calculate this, we are not able to fit exactly what we need. Um,
3.17 is the unit. What is the unit for that?
no, it's not a unit. Is the beam source like according to array size.
Okay,
For
okay.
example, how I do is like I from the macro, then from the solver, and then I can go to source, and then I have Gaussian beam.
Gaussian beam. Oh,
Yes.
great, great.
So the 3.5 is this one. Is mean
Okay,
beam
relay length.
radius.
Radius. Okay,
Is
okay,
this.
okay. Ah, yeah, yeah. That is what I was telling. So Gaussian beam will have a radius, right? It's a kind of
Exactly.
okay.
Yeah, it's just kind of radius. So for example, this is the distance, the focus distance.
Yeah,
You can see from here.
yeah. Focal
Uh,
distance. Okay.
yeah, this one.
But you put micrometer, right?
Yes,
You put
because
micrometer.
because it's like a micrometer. Something.
No, no, no. No, 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 no. Oh, okay. They have put like that, but
Yeah,
maybe Gaussian beam we can leave apart. Main beam radius. No, you're calculating using this one, right? Correct. So
exactly. This is the equation
okay,
I use, and this is like the wavelength. I can just change according to my frequency and number
okay.
of simples I want. But because for example, this one I just took 5, but you can took more as long as you
Yeah.
want. So to have a good shape, we
Correct,
can
correct,
also
correct.
change the distance, the focus distance, and the mean radius. This mean radius that we need to use MATLAB to calculate. Because if we did not respect it, it will not. It maybe give the size of the array
Got it, got it,
of
got it.
the
See,
Gaussian
according to the
will be.
size, see, according to the
Yes,
size as well as the focal distance, this has to be modified, right? Actually.
exactly. And
Mm,
also this one, like the truncation error, we need also to calculate the error
okay,
like from this one.
okay,
So actually the default error is like 0.9999.
okay. That's okay. No problem.
So from this, I can get this one. It will give me, for example, for array of 200, which will
But
be like
in
0,
this, no,
0.2.
in this what I can see that it is a single value, right? Single value, correct?
Yes. So it will give me the value of P1 and P2, the distance from P1 and P2. And then after doing my calculation from here, I can do calculation from here and here to get array size. So just
Yeah,
replace it and then it will fit automatically.
yeah.
So that was part of something that I would like to show you. But I think
Okay.
that was not our today topic. Maybe I going just to delete it I can delete this
So
field.
what you can do is, one thing is, if you are exciting plane wave, this is the one. Okay, just above the reflectory, we have to
Do you,
excite and
my
then
question
see.
was, my
Yeah,
question
please,
was,
please.
do you think practically, is it good to feed a ray with plane wave? Practically,
No.
is it
Practically, it's not possible because see, the thing is the
okay?
focal distance. We are maintaining. See, focal distance. We have a taper, right? Correct. Actually,
Yes.
it will not be a plane wave. Shall we? I think in some of the videos I have discussed that also. So
Okay.
can I show you that
Yeah,
in
sure.
Paint? Yeah, yeah,
Okay.
Paint. I will show you that one. So one of the video, I just explained what is feed tapper and other stuff, right? Okay, feed
Yes.
tapper and other stuff. Okay. So, for example, you have a horn like this. Okay, for example, horn, yeah, horn like this, right? So,
Yes.
you will have a radiation pattern of this horn. For example, you are keeping this horn after some certain distance, focal distance. Let's say, okay,
Exactly.
the focal distance, right? For example, let's say it is F, okay, and this
Okay.
distance is, let's say, D. Okay, D. If you take, tan theta with respect to this axis, right? You take tan
Yes.
theta, it will be D by F, right? Correct? Okay.
Yes.
So you will get, for example, if you want to see what is the excitation I'm getting over here, it will be according to tan theta, theta will be, for example, let's say 25 degree, for example. Okay. Let's say
Yes.
for 25 degree. Okay. Now, so this is the general pictorial representation, depends upon the position of the horn and position of the reflector ray and position of the element. Correct? What
Yes.
excitation I will get. But now, so how can I interpret in terms of radiation pattern? See, here I will have some kind of radiation pattern like this, right? Correct.
Yes.
So in 25 degree, what value I am getting? That I have to see in the radiation pattern. For example, it can be -10, it can be -9 or -15. Correct. So that taper,
Yes.
no, we can maintain only with this kind of beams. Correct. Gaussian beam
Yes.
analysis or whatever you can do. Okay, but it should be like this. We can control the taper as well. Okay. So ideally, what we
Okay.
have to do is we have to give a parabolic way of distribution, so that for example, it is actually reflector is what? It's a planar parabola. That's all. Because planar parabola, right? Planar parabola that will add phase to it. That's it, right? Because if you excite a plane wave, no, then what you will get is, for example, you have designed this as a parabola, correct?
Yes.
Reflector as a parabola, right? But it will give a parabolic shape only, correct? That phase values will be in accordance. So that's why we have to analyze with this kind of analysis. But plane wave, just to ensure that whether my and the particular position my element is giving that particular phase expected phase or not, that we can ensure by exciting the plane wave.
Okay.
Yeah, that is the one I wanted to tell you. Yeah, please proceed. Sorry, I was,
Okay.
maybe you might have, I thought of asking something, but I was explaining different thing. Okay.
No,
Yeah.
no, it's correct, sir. So that
Okay.
was part of the question I was asking.
One more thing. Can
Uh,
you zoom this, please? Can you zoom this, please? I see some kind of ambiguity here.
yeah, there is
There is
some
a overlap.
ambiguity. I'll
Overlap.
try to I'll try to fix it. I'll try to fix
Yeah,
it. It's
yeah.
just
It's
something that
basically, because of interelement spacing or something like that, it is
yeah.
getting.
So it's
Yeah.
just element size as just give it something like that. So
But
I
even
can
though
fix it.
element
But
size,
this one
but it
is
should not be
just
over. It should not be overlapping, right? But I don't know, because unit
no.
cell size you
It's
consider is lambda/2, but I don't know how
yes.
it is overlapping. Okay.
I can fix it. It's just some kind of some problem. So maybe I need
Okay.
just to restart the computer because it has been a week. I did not
Oh, sorry.
restart it.
Okay.
So that's why
Yeah.
it's giving us. But this one is just for demo for us to to understand what we are going to do.
Yes.
Do you remember last time we did one array? We feed it
Yeah.
uh with um we use discrete port, but it
Correct. Correct.
gives yeah it gave some kind of result, but I don't know where I just
But that itself it we got clear, right? Because it is not giving as expected, right? But it should not be a
Yes.
because we have to only excite with the wavegate port. One another approach is
Okay.
there because we know horn antenna we cannot excite. See, discrete port is for the mainly to excite the coaxial connector basically. Okay, not on
Okay.
this one because where you have a dielectric as well. Okay, we will excite in between that. Okay, so that you can have a potential difference, right? Correct.
Yes, sure.
In the coaxial connector, you can have a potential difference. Inner conductor, outer conductor, you have. But here you don't have any inner conductor, outer conductor concept, right? It's a single conductor, right? That is why it is not.
Yes.
It is giving wrong results. Okay, so you have to go for
Yeah.
necessarily go for waveguide port. But one another option is there. What you can do is you can configure the SMA connector on the top of it. Correct? Waveguide
Okay.
SMA connector. Like not a SMA connector, so it will be NML connector on the top of it. Usual waveguide, right? If you just go to any waveguide port, no, just sorry if you don't mind, I will just
It's
show you
okay.
waveguide. See here, you see here.
Yes.
If you model this kind of thing, then you can use a discrete port. Then you will not face any problem like offset feed or anything. It will not be a problem.
Okay.
You can just model, for example, you can just model this waveguide flange and everything. Correct? Okay. You
Yes.
can based on the data sheets, whichever band you are working for. You just model this, and then on top of this one, for example, on top of this one, just behind this one, you just fit it.
Yes.
That's all. That's all. Behind this horn under, you just fit it. It's just like adding this waveguide part will come over here. That's it. You just add it. Then you don't have any problem of, for example, axis change. Nothing. You will not have any problem because this one, no, you can excite with the discrete port as well.
Okay.
That is also
Okay.
possible. Or
Okay.
you can even try with the waveguide port as well. No problem. It will not be a problem. But first,
Okay.
what you can do is see, you can take any horn antenna, which will have a standard results only, because it's X band, Ku band. These dimensions are defining this X band or Ku band or whatever it may be. Okay, A and B. Okay, so
Yes.
basically it's almost a lambda by 2. That's all. Okay, lambda by 2, almost a lambda by 2. Okay, that only decides this one. So because in waveguide, waveguide how it works. Where is that paint?
It's here.
Oh, sorry.
Yeah, it's here. Yes.
Waveguide, no. How it works is, let me tell you. We have to excite the T10 mode, right? T.
Yes.
This is the mouth. Okay, this is the mouth. Okay, so we have to excite the T10 mode like this. So it will be E field will be like this, something like this. In general, but we have several other modes as well. But we are talking only about this. Okay. So how it works is, see, in waveguide, no, either we can use wave port like this, or we can have a waveguide like this. And then in this, no, see, in general, we'll have a waveguide, sorry, SMA connector or the N-mail connector like this. And here what will happen is it's actually a monopole. So it will radiate. This distance will be lambda by 4. We have to optimize this distance for a bandwidth. And then so that, 90 degree, 90 degree, this will be a 180 degree, right? So that you will
Hmm.
have a 0 degree. Then wave will start propagating in this waveguide, basically.
Okay.
So that's how
Okay.
waveguide principle, working principle. Okay. So you have a monopole. It's a pin only, but it will act as a monopole. It will radiate. This way, see, some waves will go directly like this. Some waves, gets reflected from this mouth, right? So it will come back. So this distance is approximately lambda by 4. So that 90 degree it is coming over here, and then get reflected by with the 180 degree, 270. Then it will again reflect back with the 90 degree. So 270 plus 90, it will be 360. So all will be in same phase. That's how it's a layman language it will work. Okay. So
Okay.
that's why we have to model like this, and then we can do this. So that's also possible. We can do this. So the data sheet now you will find it in any website. Okay, maybe
Okay.
MI microwaves and many Nardas, many companies are there. They make this kind of standard waveguides basically.
Oh, that's good.
Yeah.
That's good.
If we are using
Okay.
this case, no, you don't have to bother about access or anything. You can say, means a feed, you can offset the feed any direction that you want. By just, in a semiconductor, no, we can excite with the discrete port as well. No problem. You will get the same results. First, what you have to do is you have to model this waveguide and then observe the results. Okay. If your
Okay.
expected band is getting, you have to reproduce the results. Then you can just, fit this behind this one, fit the waveguide flange behind this one, and then evaluate the performance of horn separately. Okay, separately. Then what you can do is once you get the desired performance, here you can just optimize your horn dimension in order to get the, for example, if you are expecting some taper of, for example, in 25 degree corresponds to some element location.
Yes.
If you are expecting, yeah, for example, 30 degree, 25 degree, you are expecting, let's say, let me put a marker here. Okay. So here you can see, if you click on this marker, 345 means, 25
Yes.
means I have to put 335, right? Here, what value I'm getting? What
Yes.
is the value I'm getting? 6 plus 6, right? Okay.
Yes. Plus
So
six.
plus six is always no, we will normalize this one. We will normalize this value so that we'll know what is the plot mode, use current max, apply. It will be normalized to 0. The maximum will be 0. So here you can see minus 12 degree I'm getting.
Yes.
12 degree I'm getting, right? So that is the
Exactly.
taper I'm getting. So, if you have to design your horn antenna for the particular tapper. So, an edge, what tapper I mean, edge tapper is what tapper? For example, edge tapper means, so you have a horn like this, and then you have, a reflector like this. So,
Yes.
at this edge, at this edge, what is the tapper you are expecting? That's what, even Gaussian beam analysis also will boils down to that only. So what taper
Mhm.
I'm expecting, accordingly your wave, feeding like the source, feed source, no, shape radiation pattern will vary.
Okay.
First, you have to finalize this horn design first. Okay, if you are
Yes.
expecting, for example, 25 degree, what fade taper I'm expecting. Okay, then once you complete this with the design of horn, once you are getting certified results and whatever you are expecting you are getting, yeah, then we can import this onto that array environment, and then you can do whatever you want. If you have this kind of structure, no, you don't have to bother about waveguide port at all. Just give excite in this port, no. Just you can give inner to outer conductor. You can just give discrete port and then start working on that. No problem.
Okay.
This is another solution we have. We have discussed multiple solution. One is just making the reflector offset,
I think
just
what you are saying,
tilting.
what you are
Yeah, tilt.
saying is like, I'm saying, let me show you. Someone did something like that.
Yeah, please, please, please.
Mm, actually, is I don't know which paper. Is it this paper? Something like this, right?
Exactly, exactly. Can you see here? Yeah, exactly. Can you see here? See there? Can you see
Yes.
there? Can you zoom out, please? Zoom a bit, please. I will show you. I will show you. I will show you. 1 minute. 1 minute. No, no, I will
Okay.
show you. Can you see here? They have modeled this SMA connector, right?
Yes.
Oh, sorry. In this also any feed designer. So can you see here the feed is
Yeah,
you
use
see
the
here
spread port.
this kid code. Yeah, exactly. It will work. Definitely it will work. Because I have done this. That's why I'm confidently saying
Okay.
I have designed waveguides and also this one horns and everything.
Oh, that's good. That's very good. Okay, just something I want to show you. So actually, are we going to try to rotate? Hello, sir, are you there? Oops.
Oh, sorry. Can you see my screen? Yeah. Sorry. Can you? Yeah. Can you hear me?
Oh, yes, I do.
Yeah. 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 Please.
What I'm saying is like now can we try to fix this one, this one? For example, we import it here and we try to see to do what the technique you just
Yeah.
told me now, if we
No
can.
problem. No problem.
So I can give you
Yeah.
the
Please.
hand. I can give you the
Please.
hand.
Uh, okay. Can you import this horn first and then place it in the normal direction? Then we'll try that as well.
Yeah, I just do it manually. Like I usually like do it manually this way because it's fast.
Yeah. Can you move that? No. Okay. None. Yeah.
You can transform it. Yes, 150. Yep. Yeah. No need to rotate it, right?
Yeah. No need to rotate.
Oh,
No. I think you are going in a different direction. Opposite direction. You have to give
yes.
minus 150. That time itself. No. Go to that only. Oh, wait. I will do it. I will.
Okay.
Can you see now? Oh, why it's not reflecting?
See, the computer is
Oh,
making a little bit noise. But it will come.
okay.
Oops. Hmm. Why is doing this? Okay.
Yeah.
Oh, what's wrong? Maybe this one has discrete ports, right?
No, 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 not
Oh,
discrete board.
this is what we did last time.
Yeah,
Do you
what
remember?
we did last time. But
Discrete port.
yeah,
So I can
you will
delete it,
get some
right?
results. You will get, yeah, you will get some results. Yeah. You can delete it. Discrete board, you can delete it. That's it.
Okay.
You can move back that horn to same original position.
Do this one.
Yeah,
I think it's
means normal position. Okay. No, I'm telling
yes.
about
I don't know
the other
why
one. Oh, it's okay. It's okay.
we
Now
can
you can go to the
we
other
can
one.
use this one.
Yeah,
I
yeah,
can
yeah.
delete it.
No, what you can do is see what I'm doing, what I'm telling. Horn, you might have that did the translate, right? You can make it 0. That's all. Just 1 minute. Here you put 180 degree. Okay, that's okay. This is okay. Oh, this is also very slow. Translate. Oh, this is also fine. This we can make 0. This we can make 0. Okay. Correct.
Yes.
Got it. Got it. Now, what we can do is we can just remove the port. We can excite with the Waveguide port as well. Okay, we'll just keep like this. Okay, now I have to rotate this ground plane is what for what? Oh, you have to mingle it over here. Yeah. Okay, now I have to see, for example, I have to do first rotation. Okay. For example, if
Okay.
you want to do rotation, for example, this horn to be faced in this fashion, right? So then you
Yes.
rotate this, see, you rotate this in, for example, you can see here, um, with respect to what we have to rotate. With respect to y, I have to
Why?
rotate 30 degree.
Yes.
Oh, sorry. Can you see here?
Yes.
Now, can you see here?
Yes.
Can you see the offset horn? Offset fed reflector. Still it is
Yeah, I can
offset, right?
see.
Correct?
Yes. Yes.
Still it is offset, right? So you have to just adjust the position of the horn. That's it. With respect to horn, we have to do some math, right? So because first we have to calculate the, for example, which position I have to place the horn. This, what is the distance between this and this? So everything, what is the distance should be between this and this? So everything you have to do some mathematical calculation, and then you can do this. You can check this one, right? Now it will work. That's all.
Yes.
Oh wait.
Okay.
There it has gone. Ah, yeah. And now you can you see? Still it is
Yes.
offset, right? With respect to this reflector, it is offset, right?
Yes.
Correct? Yeah, that's it. This is what I was telling you. If you simulate, no, for example, 6,
Or if we give a approximate,
the 22, 30.
yes. Because I did not put frequency before, maybe. Because if we give frequency, it may things there is some problem with array. But it's okay. I can translate it later.
Okay.
Oh,
Port setup. What is this? Okay, we have to free this access. But it will work, definitely work. Okay. Maybe,
yes.
okay, you can just, but it's the other error, not the original one. Okay. So it will work. Definitely it will work. Okay.
Yeah.
Yeah. Can you try this one
So
and then
I can try. So what is the good techniques to reduce the calculation, yeah, like the time? Because actually,
see,
when
for example,
I simulate one like this, it takes me 3 days.
yes,
But
yes, exactly.
it's not.
See, if you are going for a central center fed, right? Center fed.
Yes.
If it is a symmetrical structure, what you can do is you can go for here symmetrical. Okay, symmetrical,
Okay.
and then depends upon the horn mouth. Okay, for example, you can see here if horn mouth is facing something like this. Okay, so this is but this plane is nothing but your E plane. Okay,
Okay.
and this plane is nothing but your H plane along this direction. Okay, so according to this direction, you have to make it as a XY plane, YZ plane, whichever for example, ET 0 or HD 0, like that we have to define.
Okay.
Okay,
Okay.
that's it. So then it will what it does is it will only simulate one quarter. Then it will replicate the results for others.
Oh,
This is
that's
also
good.
fine. And if
Yes.
you want to quickly see, okay, what I have to do, you can do what you can do is you can give highest frequency here or highest frequency here so that the boundary size will be very low, and then you can do it. That is also fine. Okay, here you can give highest frequency by means of user define. Okay, here you can
Yes.
define the highest frequency that you want. Then so that your boundary size will be low. The another method is like for example, you can just reduce the mesh size initially just to check the results, right? You can reduce the mesh
Yes.
size to 8, and here also 8, like that. And also see, this is another method. The third method is like for example, here you can see reduce the accuracy as well.
Okay.
So then just to see the preliminary results, then you can just
Yes.
once you finalize the design, then you can go for final full-fledged design, say simulation. Okay.
Okay.
And I also show you that horn reflector example, right? That you can try.
Yes.
It will give you results in 5 minutes.
Oh, that's good.
You demodel the horn separately, this one separately, import into schematic, and then for example, like this we have seen, right? Create field source coupling method, right?
Yes.
Somewhere, yeah, that you can use. No problem.
Okay. Okay.
That you can use.
But the problem of that feed source, it's still need you still need to to have a like extension, I think extension port, something like that. Because I tried
Yeah.
again yesterday. It's need to add some yeah, it's need to add port. I don't know where I was need to add source port. I think
Yeah.
excitation
So
signal. Yo, there is a
yeah.
station signal.
Yeah.
Okay, I got
Yeah.
another
Please try
question.
this. Yeah. Please try this. Maybe we'll connect tomorrow morning your time. Okay.
All
So
right,
that Yeah. Yeah.
all right. Thank you so
Yeah.
much, sir.
Thank you so much.
Thank
Bye
you,
bye.
and have a
Yeah.
good night.
Yeah. Yeah. Have a good day for you. Okay. Thank you so
Thank you
much.
so much.
Bye. Yeah.
Thank you.